exciting times. Ketones and aldehydes, our next chapter. As I put these slides together, I noticed we've already learned a lot of these things, but there's plenty of new things. So carbonyl, carbon, carbonyl, sometimes people say. What compounds have carbonyl carbon? Ketones, carboxylic acids, esters, aldehydes, acid chlorides, I'd say acid anhydrides, looks kind of like an ester maybe, and amides. All these things have a double bonded carbon. So we say both these atoms are sp2 hybrid, leaving the leftover p orbital to form the double bond. We see that the carbonyl bond is a little shorter than a carbon-carbon double bond. And sure enough, the shorter the bond, the stronger or the more energy that's in it. So there's our carbonyl bond trivia. Can you draw a resonance structure? Draw all those electrons jumping up. We'll have this. Draw all those electrons jumping down. And it can go back and forth. Probably the best thing we just saw with what kind of director is carbonyl carbon on a benzene ring? Ortho, para, or meta? Yeah, it's meta because of this partial positive charge, partial negative charge. Put this on a benzene ring. Oh man, I'm not batting 300 with my drawing today. So let's just make that a ketone. Yeah, when you things electrophile hits in the ortho and para, you get that positive charge in the sigma transition state. Nature doesn't like that. So I really like the partial positive, partial negative. You know, this is the major contributor. And we say it's an electrophile. Carbonyl carbon is an electrophile. And if we protonate the oxygen with a carbon, it makes it even a greater electrophile. So in the Fischer esterification and in the aspirin synthesis, you had an acid catalyst. The acid hits right there on those protons. So how do we name ketones? We basically name it as an alkane, chop off the E, and add 1. All right, so here's a 1, 2, 3, 4 carbon chain. So instead of butane, we go butane-one, and we put a 2 out in front to say the second carbon is the carbonyl carbon. And that's the old IUPAC, which I like. It's old. And the old IUPAC could only put this back inside the name if it was needed because of other substituents. Most of the time it's obvious, then when it's not, they move it. All right, so here, what do we got going on? 1, 2, 3, 1, 2, 3. Looks real symmetric. 2,4-dimethyl-3 pentone, or 2,4-dimethyl-pent-3-one. 1 phenyl propane 1-one. So we want to give carbonyl carbon the lowest number. Don't want to go from that end. Don't want to go from this end. Don't want to call this 3 butone. Name it as an alkane, chop off the E, and put in the word 1 or own. How about naming cyclic ketones? Carbonyl carbon gets assigned number 1. It has priority over most other groups. Like a double bond, the carbonyl group has priority, so we don't start and go 1, 2, 3. We're going to give this the 1. So cyclo 2-ene-1-one. And I guess here the old IUPAC and the new IUPAC's well, we don't need to tell the reader it's at number 1. The 3 implies it's at 1. So 3-methylcyclopentane-one. And here we have an alcohol group. And the carbonyl carbon has precedence over an alcohol. So we don't start numbering 1, 2, 3, 4, 5 that way. We start over here to give carbonyl carbon the lower priority. And we name this as a hydroxy substituent. 4-hydroxy 4-methylpentane-2-one. That about covers it, I think, for nomenclature. Any questions on the nomenclature? Ketones. I think we'll get to aldehydes second here. So I always have to really think about this, not the concept, the enunciation. This is ethanol. This is ethanol. Ethanol. Oh man, I already screwed it all up. Uh, ethanol. Ethanol. There we go. I figured out in life half my spelling problem was really pronunciation. All right, so aldehydes have high priority. They only end up at the end of a chain. We like to give them number one, and we basically chop off the E of the alkane and add Al. Ethanol, ethanol. There, I should have practiced before I came in this morning. This has a common name. Does anybody know what it is? Acetaldehyde. Think your acetic acid. All common names there. So here we got a bunch of substituents. This is always number one. 4-bromo-3-methyl heptane all. 3-hydroxybutane all. All right, now here's something interesting. Maybe we have it down here. If the aldehyde group is attached to a ring, the suffix carbaldehyde is used. And so here we got cyclohexane, so we just say cyclohexane carbaldehyde. So a special case, you got the aldehyde group as a substituent, typically on a ring, because otherwise it would come out like these other things. We just name the ring. All right, so we got that under our belt. Let's put a group on here like the hydroxy. We should also have a double bond or something. Yeah, that would be interesting. Put the double bond here and ask, do I go around that way or that way? We don't have to do that on this one. Aldehyde has precedent over an alcohol, so we go this way around the ring. So then we go 2-hydroxycyclopentane 1-carbaldehyde. Any questions on naming aldehydes? Any questions on the enunciation, since I'm now an expert? All right. Carbonyl as a substituent. So some interesting things going on here. We got the ketone and the aldehyde. Aldehyde's going to have precedent. So we'll count 1, 2, 3, 4, 5. So pentane, chop off the E, add Al. So we got pentane all. And so this named as a substituent is 3-oxopentane all. Hopefully we'll get to the carboxylic acid chapter this semester. It has priority over an aldehyde. And so we have benzoic acid. We name an aldehyde. Does this make a liar out of me? Seems like I could have gone benzoic acid to carbaldehyde. Guess we don't do that. We use this formally. 2-formally benzoic acid. So unfortunately here, we maybe have to learn the carboxylic acid naming convention. You chop off the E and you add oic acid. So this is 4-carbon chain, this is butanoic acid, and now we got these two substituents. So we go 3,4-dioxobutanoic acid. So I guess the reason why we don't say carbaldehyde is due to that we have a higher priority group. Of course, if this was a hydrogen, I would call that benzaldehyde. So since this has a higher priority, the ketone gets named oxy, and the aldehyde is a formally group. Aldehydes have higher priority than ketones. Our common names, kind of similar to the ether. We name the two alky groups methyl ethyl ether, and here we got disec-butyl ketone, and then there's this Greek alphabet convention where this is, we don't count this as 1, we count this as A, B, C, but alpha, beta, gamma. So beta, bromo, ethyl, isopropyl ketone, tet-butyl, alpha, methoxy, propyl ketone. Greek letters instead of numbers. Historical names, acetone. What's the IUPAC name for acetone? Let me do the old IUPAC and the new IUPAC. 3-carbon chain, 2-pro pain, drop off the E and add new IU pack. The only one I care about is probably knowing that this is acetophenone from our benzene chapter. All right, physical properties. It all comes down to intermolecular forces. And I suppose I should have brought in my calculator. Why is this one so much more than the rest? Notice 3 carbon chain OH. So there's a slight difference, a few less hydrogens with those than the rest of these. Looks like we almost have, these are constitutional isomers. Why is this one off the map? 97. That's almost as much as water. Boiling point, 8 degrees Celsius. You got to have that in a gas cylinder. Methyl ethyl ketone or methoxyethane. What can this thing do that the others can't do? Please tell me. Hydrogen bonding. Right. Ketones and aldehydes are more polar, so they have a higher boiling point than the corresponding alkanes or ethers. So here's the ether, here's roughly an alkane. I think they roughly have the same molar mass. So London dispersion forces are about equal, but we have, dipole here, hydrogen bonding here, and aldehydes and ketones can't hydrogen bond to each other, so their boiling point is much lower than comparable alcohol right there. Now water can hydrogen bond if we get a mixture. So you can imagine, as long as these alky chains don't get super long, we're going to be somewhat soluble in water. Good solvent for alcohols. Here's the alcohol. Acetone and acetaldehyde are miscible with water. What does miscible mean? It can dissolve in any proportion. Immiscible means not soluble in each other. So formaldehyde is a real interesting compound. Here it is. Now you can't just buy a bottle of that. It doesn't really exist like this. You can buy a bottle of formalin, and the chemistry we get into this chapter is this thing called hydrates and acetals and hemiacetals. Big thing in your carbohydrate sugar chemistry. So if you just try and get this alone by itself, it'll either be this or kind of a mixture. This is called para-formaldehyde, a polymer of formaldehyde, a little bit of heat. You get this, and look, boiling point, negative 21 degrees. That's why you go over to the biology department, you might say it smells like formaldehyde. They have dead animal samples where the animal is in a solution of formalin. So formaldehyde is a gas at room temperature, but what you buy when you get it from the chemical store is formalin, 40% aqueous solution. So I believe that means 60% water, 40% of formaldehyde, and it exists as this thing called the hydrate. It's a foreshadowing of great chemistry to happen in this chapter. Trioxane is a cyclic trimer of formaldehyde. When trioxane is heated, it generates formaldehyde. Melting point. Interesting. So this is a solid and this is a gas. Interesting thing is why are these things the way they are? Hydrates, acetals, and hemiacetals. That's all the chemistry of carbonyl carbon, which we should get in this chapter. So we rehash a lot of things you've already learned about, like our IR spectroscopy. I always say 1720. So here's the stretching. So that big slag type in the middle of the IR spectrum, you can't miss it. It's carbonyl carbon. And then depending on how it's set up, by the way it shifts a little bit, you can tell an ester from a ketone. Aldehyde's going to have this stretching here. Man, that's awful close to that carbon hydrogen on an sp3 hybridized, that one slag type that I say every carbon compound has. But typically you'll see this has a little spike on one side of that. So carbonyl carbon's a very strong stretch, around 1710 for ketones, 1725 for simple aldehydes, and an additional carbon hydrogen stretch for aldehyde, 2 absorptions, 1710 and 2810. Now I want to go back and look at some spectra. Well, this is a bit of ways from 1710. So it's this. Ooh, this one's higher. Oh man, look at that. 1815. So this thing here, now that you know about all these double bonds, there's some conjugation there. Conjugation lowers the carbonyl stretching frequencies to about 1685. And these get increased, probably due to a bunch of angle strain. Rings that have ring strain have higher carbonyl stretching frequencies. Proton NMR spectra. So this one's always pretty good telltale sign because it's highly deshielded. Shows up way downfield on the left between 9 and 10. Can't miss it. So alpha carbon, some of that Greek nomenclature. So it'd be the alpha carbon. Usually absorb between 2.1 and 2.4 if there are no other electron withdrawing groups nearby. Well, that's a big range. I don't know if that's going to help me a whole lot. Notice this one's more shielded than this one. They're both being deshielded by carbonyl carbon, but this thing's getting deshielded. It's a methylene carbon or methylene protons instead of methyl protons. So let's count 1, 2, 3. So this is actually kind of a triplet, right? Being split by those. And this one's way over here, 9.9 or something. And why did they tell me these skills? All right, protons closer to the carbonyl carbon are more deshielded. The alpha, beta, and gamma protons appear at values of delta that decrease with increasing distance from the carbonyl group. So here's our triplet. Here's a 1, 2, 3, 4, 5, 6. That makes sense. 3 and 2 is 5 plus one more. And this thing, 2 and one more make 3. Should be a quartet, but there it is. Looks like a triplet. We won't try and make much out of that. So here's the carbon NMR. Now I kind of like this one. So I got 1, 2, 3, 4, 5, 6, 7. What do I got going on here? 1, 2, 3, 4, 5, 6, 7. There's your TMS. Makes sense. That's all for today.